Welcome to constant solutions of separable equations. So recall a separable equation can be written in the form h of y times y prime is equal to f of x. And we saw then that we could find solutions. We can find solutions by integrating both sides. So we had the integral of h of y dy is equal to the integral of f of x dx. And I'm going to write the plus c just to show that we have it. It turns out that not all solutions have to take this form. So it turns out that not all solutions have to take this form. So we're going to consider a special case. Let's go ahead and look at equations of the form y prime equals g of x times p of y. Right? So y prime equals g of x times p of y. We can rewrite this. So this can be rewritten in more standard separable form. So we can rewrite this as 1 over p of y times y prime is equal to g of x. And so as we saw previously, we can find solutions where we have the integral 1 over p of y dy is equal to the integral of g of x dx plus c. But in the rewriting from that first line to the second, we actually do lose a little information. So in this line, the first original equation, y prime equals g of x times p of y equaling 0 essentially is allowed, right? In the second equation, this equation no longer makes sense when p of y equals 0. And so p of y cannot equal 0. Our solutions don't apply in that case. So we lose potential solutions involving places where y would satisfy p of y equals 0. So in rewriting the equation, in the new form, we lose solutions y equaling y of x such that p of y equals 0 for some x. So let's go ahead and just look at that situation. So suppose that p of a is equal to 0. About that, my screen stopped updating. So again, let's suppose p of a is equal to 0. Then what we would get is if y of some x value. So let's just say y of x naught is equal to a, right? Then what we have is that y prime at x naught would be equal to g of x naught times p of a, and we get 0. So for any x value, if p of a, or sorry, for any x value, if y evaluated at x is a, the derivative is 0. That means we could use the constant function. So this means that y of x equaling a, or y 3 lines set equal to a, is a solution to y prime equals g of x times p of x, sorry, times p of y. Again, this would hold true because the derivative of that, right, we'd have if y of x is equal to a, then y prime of x is equal to 0, and that does satisfy y prime of x is equal to g of x times p of a, also equals 0. So key thing here is if p of a equals 0, then the constant function is also a solution. So we've been ignoring this when solving separable equations so far. So let's just go ahead and throw our constant solutions in. So in this example, y prime minus 3x squared y squared equals y squared. We can rewrite this in the form y prime is equal to y squared times 3x squared plus 1. Previously, we found solutions y equals -1 over x cubed plus 2x plus c. So now we need the constant solutions. So for the constant solutions, y squared was acting as our p of y. We set that equal to 0. We get that y equals 0. And so our constant solution would be the constant equation y is identical to 0. So here we have solutions, the ones we found previously, and the constant solution y equals 0. Let's look at one more equation we previously worked with. So if y prime over x squared was equal to y minus 1 times y plus 2, we can rewrite this as y prime is equal to x squared times y minus 1 times y plus 2. Previously, we found solutions of the form natural log of the absolute value of y minus 1 over y plus 2 is equal to x cubed plus c. If we now look for the constant solutions, we are looking for where y minus 1 times y plus 2 equals 0, or y equals 1 or -2. And so our constant solutions would be y is the constant 1, or y is constantly 1, or y is the constant equation set equal to -2. So again, we have the ones we find via integration, but we also have these additional solutions, constant solutions. Y is identically 1 or y is identically -2.